Yeah, welcome to Numerical Methods for Mathematical Finance. And we started our nice section on computer arithmetic. So when we started this section, we came from the motivation of the Monte Carlo simulation. And there one important application was to calculate the average of a random variable. So the average of the random variable is approximated by 1 divided by the number of samples. Take the sum over all evaluations on these samples. So we need to calculate a sum. And what we had was a small teaser for the summation. So it was that we calculate a large sum, so the 10 million summations of a small value. So that's here, yeah, so run over these 10 million evaluations and sum the small value. And then we were calculating the average, and the average is divide the sum by the number of values. Okay, and let me run this summation teaser again. And you saw that if you make the sum, the number of summations very large, the error is growing and growing. Yeah. So for example, for say just 5 summations, there was no error, but already starting at 10 summation, the average of always summing 0.1 divided by the number of summations should be 0.1, but now we get an error already for 10 summations. And if you make more and more summations, say 10 million, you get larger and larger error. But now you know why this is happening. So this is happening because here, if the sum is becoming larger and larger, you are adding a small number to a large number. And you have this effect that you have a relative error, but the relative error is relative actually to this large value. So in absolute terms, the error is becoming larger. So with respect to summation, and as an application in mathematical finance, we have here, for example, the Monte Carlo methods. We have the problem that if we would like to approximate this expectation with the sum, then if we take here this naive implementation, it would look like that. So my random variable is, so now I like to sum values, say xi, which are a random variable x of omega I, and in the computer it is maybe represented here as this realizations of I. So this here is your vector x. So I maps to x of omega I, and you would like to calculate now the average. So what you do is you define the sum, you sum over all these realizations, and you calculate the average. So you return the sum divided by the number of realizations. So now we have this problem that we are accumulating here larger and larger errors. And let's do this as an experiment. And then I show you how to fix this. So maybe I create here a new class. So maybe I just copy my teaser now to summation experiment. Okay, so this is here my summation experiment. Well, maybe let's make the code a little bit more flexible. So this here is my value, and this here is my number of values, and then we have a function, and this function calculates the average for us. So this is the average in the classical way. So, and I would like to sum this value, number of value times. Okay, and he now complains that he does not have this method, and I just copy the code here that calculates this average in the classical way. Okay, so now I just moved my code to a function. So that is now my summation. Oh, sorry, I'm in the wrong class. Let's fix that. This is my teaser. This is my summation experiment. Okay, so let's run this experiment now. It's just the same, but I would like to fix now this problem. So this is the average using the classical method. Okay, so that experiment is just what's written here. I calculate the average 1 divided by n xi. Oh, small typo here. This should be I from 0 to n minus 1 xi. Well, and I calculated here for c equals 0.1, so all the values are the same, and I use 10 million. So now there is a way to fix this. And this method is called the Kahan summation, which I would like to introduce now, and which we will also use in our implementation then of the Monte Carlo average. Actually, this guy, Kahan, is also the guy that defined this IEEE floating point standard. So you can also read a lot of this about this summation method in the reference I gave you. And the idea is actually quite simple. So think of what is happening if you have this problem that 1 plus epsilon is 1. So assume that in your summation you have, say, a large value, say 1, and then comes a small value. Or for example, the sum is already accumulated to a large value, and then comes a small value. So what you have as a result is x0 plus x1 is 1. So 1 plus epsilon is 1. So you made this error. However, you can check the error. So what you can do is you can check what is actually z1 minus x0. So z1 minus x0, okay, this means I move this to the other side. This should be equal to x1. So what you get if you do z1 minus x0 is, well, you have the wrong solution 1 here, that was rounded. 1 plus epsilon was unfortunately rounded to 1. So z1 is 1, x0 is 1. So I get a 0 here. Now, if you now subtract from that the x1, so you compare this difference to what you would expect. So what you would expect is that this is equal to x1. So the next step is that you do z1 minus x0, and you would expect x1. Then you get, okay, this here is unfortunately the wrong value. This is a 0. So this should be 1 plus epsilon, but it is rounded to 1. So maybe I should not write equal, maybe I should write like that. Or I should maybe write that here the float rounding around this result is performed. Okay. So maybe I make the slide precise. So my operation is that z1 is x0 plus x1, but then this is rounded to the next floating point number. Okay, so if you now see what is actually the difference of z1 minus x0 which is rounded to then 0, yeah, so Z1 has been rounded to 1, Z1 minus X0 is 0, and you subtract what you expect, you see that you get a minus epsilon, which is minus the error that you have here. So there is a way of finding out what is the error. And what we will do now is just we track this error. So we calculate this error and we accumulate the errors. Because you see that the error that we have is small. We will make many small errors. And if we accumulate these errors, the errors will become larger and larger. And at a certain point, the error is large enough that we can push it to the summation. Yeah, so the rounding is not consuming the error. And this is the main idea of the Kahan summation algorithm. So I have the summation algorithm here, and maybe I mark first in blue the classical algorithm so that you see actually that we are doing the classical stuff here with a small modification. So as for the classical algorithm, I start, So as for the classical algorithm, I start with initializing my sum to 0, and I'm looping over all entries of my numbers, which I have to sum. I fetch the number which I have to sum. So this is here my xi, yeah, my i's entry. And then I'm calculating the sum plus this value, and this is my new sum. So, and in the end, I update my sum variable, sum equals new sum. So you see, this is really the classical algorithm, except that I wrote it a little bit more lengthy. Yeah, so you could just remove this additional variable here and say that sum is equal to sum plus value. And now I make a small modification. And my modification is that I would like to track the error. So I define what I had on the previous slide, the new sum minus the previous sum. Yeah, so this should be value. Okay, this should be value. And then I just subtract the value because that is then my error. Okay. So if error is negative, what does it mean? If error is negative, it means that this number here is smaller than value. So it means that the new sum is smaller than what the sum should be. Yeah, because you can also write this as new sum minus sum plus value, yeah, in brackets. So if error is negative, the new sum has been too small. Yeah, something has been lost by adding these numbers. So this just means that I would like to remind this and add it in the next iteration. So adding it in the next iteration means that we add minus error, yeah, because if error is negative, yeah, minus error represents what has been lost. So we add minus error to compensate for the previous loss. Okay, yeah, you can also define error as value minus new sum minus sum, yeah, then it will be a plus on top. So you see that you have now these two modifications. So you have a running error. So this error somehow can accumulate. Yeah? So you have a running error here. And I'm subtracting the previous error here from the next value that has to be added. And here you also see the nice thing that the operation that you now make on this error, yeah, so you have calculated more or less quite precise, yeah, because this here is a small number and this is a small number. So the error is the epsilon 10 to the minus 16 times the small scale. So the error is small. So you have calculated quite accurately up to 10 to the minus 16, the error. And then you fix the error on the next iteration, but this here is also a small number, yeah, if you are adding small numbers. So I fixed this on this small number. Let's implement the Kahan summation and let's check what is happening to our small experiment. So I calculate now the average using the Kahan method. So I sum number of value times the value, and let's print this result averaged using Kahan method. So this is this number. Okay, so of course he complains, yeah, I do not have this method, so I need to implement this method. Yeah, and this method is now just my modification of the classical algorithm. I'm a bit lazy. Let's copy this code. So what I have to do is I have to introduce my new running error here. Okay, so and then instead of just using the value, I use now the value that is fixed with this error. Yeah, so I use value minus error. Okay, so then I'm updating my sum, yeah? But I update my sum in a way that I remember the old sum. Yeah? So I'm not overwriting the old sum. So now, since I have not overwritten the old sum, I can check the operation. This gives me the error. So the error is now the new sum minus the sum. This should be the value, actually my new value. Yeah. This should be the new value, but now I subtract the new value and I get the error. And once I have done this, then I can overwrite my sum. Yeah, let's try this program. Okay, and you see that I get the correct result. Yeah, so you can play now here a little bit with the setup. Yeah, so he has always different rounding errors in the classical method, and the Kahan summation is giving me the correct result. Yeah, so there is no. Okay, if you do this with floating point numbers, so if you have float here, so single precision floating point numbers, actually this error is really already very significant. Yeah, but already here you lose a lot of digits. So let me finish by first having a small example where you can again understand how the Kahan method works. So consider here the case where the summation is of the form that your first number x0 is 1, and then the other numbers that you sum are the epsilons. Yeah? So the machine precision constant. So you have 1 plus epsilon is actually rounded to 1, yeah, and 1 plus 2 epsilon is equal to 1 plus 2 epsilon. So this has a floating point representation. So if we have this situation that the first value is 1, and then we add epsilon, 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 this is a nice example to understand how the algorithm works. So the algorithm is again here below, and what we do is I initialize my sum to 0. So my sum is here initialized to 0. I also initialize my error to 0. So my error is initialized here to 0. And then I get the first value for my summation. So my first value for the summation. Okay. So this is the value. This is the 1. Then I'm using that value, but I'm correcting with the previous error. Okay, here there was no error in the previous thing, so I'm correcting this value by calculating value minus the previous error. So what you have here inside is that you use value and you use the previous error to calculate this guy. So these two here define this result. So 1 minus 0 is 1. So then I define the new sum. The new sum is, now maybe I use here dark green. This is the new sum. It is just the previous sum plus the new value. And then I need to check for the error. So my error is, what is the difference of the new sum and the previous sum? So my error here, what is the difference of the new sum? So that was the dark green, and the previous sum, that was maybe the light green. Okay, I compare this to the value that I have added. Yeah, that was my new value. So that was the dark blue one. Okay, and this is calculating the error. So of course, my new sum is 1. The previous one was 0. So 1 minus 0 is 1. The new value is also 1. 1 minus 1 is 0. Error is 0. So then in the last step, I update here my sum again. So I have here again the sum. Okay, and then I just copy the sum over to here and I start again. So what's happening now? So now we are adding epsilon. Yeah. So I'm adding epsilon. The previous error was 0. So epsilon minus 0 is still epsilon. The new sum is 1 plus epsilon. 1 plus epsilon is, now we get an error, is rounded to 1. So if we check this, we see that we have an error, and my error is minus epsilon, yeah, because 1 minus 1 is 0. Yeah, the new value is epsilon, so minus epsilon, 0 minus epsilon is a minus epsilon. So we have keep track of the epsilon, and the new sum is just, the sum is just the copied over value of the new sum, so that is 1. Go to the next line, you add again a small number epsilon. So, but now the new value is epsilon. So the new value is this epsilon minus our previous error. Okay, so minus epsilon minus our previous error that we have kept track of. So the guy that is here. So the new value is the value, yeah, and the error compensation. So I have that the new value is a 2 epsilon. So my new sum is now, the previous sum is 1 plus 2 epsilon. So my new sum does not have a rounding error now, because now the error has led to the fact that the value is large enough, and I have a 1 plus 2 epsilon. If I now check, the previous sum was 1. The new sum is 1 plus 2 epsilon. The difference is 2 epsilon. The value that I added was 2 epsilon. So I realized that I have no error. So we see that the error is 0. And my sum is updated to the 1 plus 2 epsilon. Okay, now you see that the scheme is just going on like that. Yeah, in one summation step, so in the next one, there is a rounding error and you keep track of it. And in the one after, this error is actually consumed by the sum, so the error correction has taken place. So you see that here in this nice example, the maximum error that we get is epsilon. Yeah? independent of how large the sum becomes, yeah, because we are always alternating between having an error and correcting it. So we can summarize this in maybe a nice theorem. So here you have for the summation 2 error estimates. So using the classical summation, we have that the sum, and this is now in mathematical terms, the exact value of the sum. The sum is actually sum of xi, but every xi multiplied with an error 1 plus delta I being then the relative error. And this relative error, we have an estimate is smaller than 2 times n minus I, so something order of n times epsilon. So you see that I have an estimate, but in this estimate, there is an n. So the estimate that I can guarantee is actually becoming worse if you sum more numbers. For the Kahan summation, what we have is also an error estimate that looks similar, so using the Kahan algorithm. But now the sum that we calculate is the sum of xi, where every xi is multiplied with an error 1 plus delta I. And for the delta I now have a much stronger estimate. So the delta I is smaller or equal 2 times epsilon. So actually, if you forget about this term, and this term here has an epsilon squared, n times epsilon squared, so this term will be small. I mean, epsilon is 10 to the minus 16, so n could be 10 to the 16, could be very large. So if you forget about this term and just look at this guy here, and you now plug in for the delta I, the 2 epsilon, so you like to estimate it, so you see that the relative error on the sum is just twice the machine precision. So you have almost exact rounding by these concatenations of summations. You do not get a much better error. You can get twice machine precision, but it's still machine precision. Here it grows. So I also have the proof for at least the first error estimate here. For the full proof, you can look at my reference. Maybe just to finish, let's have a look how you would prove the first estimate, because that's also nice. It gives you a little bit intuition how this accumulation of the error is taking place. So let Si denote the floating point number being the result of the i's summation. So that means Si is Si minus 1 plus Xi, rounded to the nearest floating point number. Note that Si minus 1 plus Xi is the true mathematical solution of this summation, is the true mathematical value of the plus operation. So what do you know about Si? You know that the plus operation is atomic, so it has exact rounding. So you will be rounded to the nearest representative in the floating point numbers. So you will know that Si is just 1 plus delta I tilde times the true solution. So this is that we have exact rounding. Because plus is an atomic operation. But now we do this in every step. So, and now if you plug in this value, so you can just iterate this, you see that the first x0 that you used while summing up is multiplied with every rounding error of every summation. So you have that an xi in your sum, in your final sum. So now you look at your final sum. There you have that an xi is multiplied with all rounding errors, starting with the first addition where the xi came in, and then the rounding error from i+1, i+2, and so on. So I have the product of all these errors in front of the xi. Yeah, this is a product 1 plus delta k. So the result now follows if you just define this guy here as my 1 plus delta I. So that's the rounding error that is in front of the xi. And that's the guy that is here in the theorem. This 1 plus delta I is exactly this guy here in this definition. Yeah? And now I have to prove that the delta I is smaller than 2 times n minus I times epsilon. Okay, so if this delta k here is bounded by an epsilon, you have here a product 1 plus epsilon. So I have actually a 1 plus epsilon to the power of n minus I. Then you can estimate this at least if n times a is small enough. Yeah, you can check if it's smaller 1/8. You can use the estimate 1 plus a to the power of n is smaller than 1 plus 2n times a. So I just use now this estimate. So I get the 1 plus 2 times n minus I times epsilon. So you see this grows because a part of the summation is multiplied with all the rounding errors of the future summation. Yeah, that was it for today. Yeah. So we did this small experiment. You have this summation experiment also in our repository if you like to play with it. And here is this reference, which has some more nice details on computer arithmetic. So that was my section on computer arithmetic. Next section will be then Monte Carlo method. Thanks for today.